Okay, hi everybody. So this is sort of a loose end that somehow fell through the cracks when I posted the lecture 20 from last year. Namely, we didn't actually define row space in any of the lectures. So let me just do that now. So suppose you have an m by n matrix. So of course we can write it as we can write it as a bunch of columns, and there are going to be n columns, C1 through Cn, and these columns live in Rm. Or we can change our perspective and view it as a collection of rows. So let's call the rows R1 transpose down to Rm transpose. And transpose because these are, they're row vectors, they're not column vectors. And these Ri are now vectors in Rn. So the row space of A, so this is the definition. The row space of A is the span of the rows of A. So it's a span of R1 through Rm. And since these vectors live in Rn, this is a subspace of Rn. Okay. So in particular, if you think of the linear transformation multiplication by ATA, then the row space actually lives in the domain. Whereas, for contrast, the column space lives in the codomain, right? So this is Rn and this is Rm. So that's the definition of the row space. And the important relation that we used in lecture 20 is that the row space is closely related to the null space. Namely, it's the orthogonal complement of the null space. And that makes sense. The null space is another vector space that lives in Rn. So I'll just draw it like this. Maybe I'll draw it in red. And this is the null space. So let me now state and prove that. So theorem, the row space, its orthogonal complement is equal to the null space. Okay, so the proof is very simple. Well, we'll just follow the definitions, right? So remember, we have our matrix that it will be beneficial to view as a collection of rows. M rows. So now, okay, so a vector, what does it mean? A vector is in the null space. Well, the definition is just that, well, AX is 0, right? So we just write it like this, R1 transpose all the way up to Rm transpose times X is 0. That's the definition. But now, just thinking about the high school definition of matrix vector product, when you multiply a matrix by a vector, you just end up taking the dot product of each of the rows with the vector. So this definition is equivalent to saying that R1 transpose X equals 0, R2 transpose X equals 0, all the way to Rm transpose X equals 0. And those are just the same thing as dot product, right? So this is the same thing as saying R1 dot X is equal to 0 all the way to Rm dot X is equal to 0. Okay. So this is just these steps are just change of notation, nothing really going on here. And now we do something a little bit interesting. We observe that if X is orthogonal to R1, R2, all the way to Rm, then it's orthogonal to every linear combination of them as well. So this is where we do something a little bit interesting. This is the same as saying any linear combination of these vectors dot X is equal to 0 for all C1 through Cm. Okay, that's kind of easy to check because, certainly the individual rows are a special case of this. And if X is orthogonal to each of the rows, then just by linearity of the dot product, just by distributing the dot product, you get that it's orthogonal to any vector in the span. But then this is just the same as saying if and only if X is orthogonal to every vector in the row space. If and only if X dot Y equals 0 for every Y in the row space. So then, that's the same thing as saying that the orthogonal complement of the row space is equal to the null space. So that's the proof. And that's maybe the easiest proof. I might as well give you an alternate proof just because, I don't know, it uses some other concepts that are useful. So this is proof number 1. Here's an alternate proof. The alternate proof is a bit more abstract. It's based on matrix algebra. And the key property we use of matrix algebra in this proof is if you have two matrices A and B, then A times B transpose is equal to B transpose A transpose. So we'll use that property, an elementary property of matrix multiplication. Well, so what's the proof? So assume X is in the null space of A. That means AX is equal to 0. And now assume Y is in the row space of A. Again, by definition, that means Y is equal to, it's in the span of the rows of A, which are the columns of A transpose. So Y is equal to A transpose Z for some Z in this case, M, right? Because A transpose is an N by M matrix. So right, A is M by N, A transpose is N by M. Okay, so these are just definitions. And what I need to show is that these are orthogonal to each other, right? That would mean that these subspaces are orthogonal complement. So need to show X dot Y is equal to 0. Because since these are arbitrary vectors, if X dot Y is 0, then these are orthogonal complement. And now let's just do some algebra. Well, we're going to use, of course, these properties, right? So we're going to have to use these two properties as well as this property. So now the key observation is that X dot Y is just equal to X transpose Y, right? But now Y is equal to A transpose Z. So this is X transpose A transpose Z by the second box, right? And now we do the slick thing where we use the property of this property star of matrix algebra to see that this is equal. We can X transpose A transpose is just AX, the whole thing transpose, right? This is the key step. But now what's AX? Well, by the first box, it's 0. So this is 0. So that's a slick matrix algebra proof of the same fact. Anyway, that's the key. That's one thing many people asked about in the proof of the fundamental theorem of linear algebra in lecture 20. So that's the explanation.